All right, so now let's talk about closed and compact sets. Well, we are going to define closeness by using the idea of neighborhood. So a set S is called a closed set if it contains all its accumulation points. Accumulation points, as simple as this. All right, so example is open interval 0, 1 closed set. Well, we previously defined an open interval, closed interval. So other than, open interval has those open brackets and the closed intervals has those closed brackets. So what is really the difference between these two sets? Well, one includes the boundaries, the other doesn't. So does that mean that, the closed set must include the boundaries? Well, not always. So here in this example, if this is my set S, well, first of all, any point X in between 0, 1 is an accumulation point. Accumulation point. How do I know that? Well, because if you consider the R neighborhood of any X in this interval, well, this is basically an open interval, X minus R, X plus R. All right. So therefore, so let's say this is the real line. All right, so this is point 0, this is point 1, where they're not included. So if I pick any point X here, so any neighborhood around it, so whether it's very small or very big, doesn't matter. The thing is, this neighborhood will always include, all right, always include some other elements in this 0, 1 interval other than X itself. So don't forget, so as R gets bigger, well, it's going to contain the entire set X, S. But if it is very, very small neighborhood, so if R is very, very small, well, as long as R is positive, which we know it is, right? Because the definition, if you remember the definition of neighborhood, R is always a positive number. Well, as long as R is positive, this interval will always include a real number other than X itself. So therefore, every neighborhood of X is going to include an element in 0, 1 interval, and hence any point in 0, 1 interval is an accumulation point. But is that it? Is this the whole set of accumulation points of 0, 1 open interval? No. X equals 0 and X equal 1, they are also accumulation point of this set S. All right, so how so? So consider the neighborhood, R neighborhood of 0. All right, so this is nothing but 0 minus R, 0 plus R, or equivalently minus R plus R open interval. So again, if you look at the real line, all right, so what I do have is the following. So if I have a real line here, all right, if this is 0, if this is 1, so a neighborhood around 0, all right, this is minus R, this is plus R. So this neighborhood will always include some elements from the 0, 1 interval, all right? Whether R is very, very small, R can't be 0, so R has to be positive. So it will always include a point in 0, 1 interval, okay? So for that reason, 0 is an accumulation point. With exactly symmetric arguments, 1 is an accumulation point. So in fact, if you call this new set S sub A is the set of accumulation points of set S, well then you're going to see that set of 0, 1 open interval is equal to 0, 1 closed interval, because everything in between 0, 1 is an accumulation point, 0 is an accumulation point, 1 is an accumulation point, so therefore everything is therefore 0, 1 closed interval is the set of accumulation points. And clearly this is not a subset of 0, 1 open interval because it doesn't include 0, it doesn't. So remember, the being subset, every element here has to be an element there, but 0 is an element here, not an element here, so therefore this, 0, 1 closed interval is not a subset of 0, 1 open interval. So, therefore, this is not an open, closed set. I'm sorry. Okay, what else? Well, let's consider the set of natural numbers. All right, remember it was 0, 1, 2, etc. So is this a closed set? Well, let's first find the set of all accumulation points. So what are the accumulation points of the set of natural numbers? Well, the quick answer is, well, there's no accumulation point of set of naturals. How so? Consider, for example, x equals 1. Is this not an accumulation point? No, it's not. Well, why? Well, again, on my set of reals, so this is the mother space. So the naturals are like 0, 1, 2, 3, etc. So they're distant from one another because I know there's like many real numbers in between them. So x is equal to 1. So this is my center. So consider a neighborhood around x is equal to 1 and r. The thing is, this neighborhood should include other natural numbers from the set of naturals for any r. Well, if r is big enough, well, it's going to cover a lot of natural numbers, obviously. So good. But what if r is small, very small? For example, r is equal to 0.5. All right? Well, in this case, so this is 1 minus r. So it's 0.5, and 1 plus r, which is 1.5. So this interval is 0.5, 1.5, is the neighborhood. So our neighborhood, r equals 0.5, neighborhood around 0.1. Does this interval include any natural number other than x equals 1? No, it doesn't. All right, it has only one natural number, which is x equals 1 itself. So therefore, this n xr intersection the set S except, the point x is empty in this case. So therefore, the point x is not an accumulation point. Here, the point x is being 1. All right, so natural number 1 is not an accumulation or limit point of the set of natural numbers. What about 0 or 2? Well, there's nothing special about x equals being 1, all right? Same arguments is going to work, same arguments are going to work for x equals 0, 5, 10,000. So therefore, the set of natural numbers, the accumulation points, the set of accumulation points of natural numbers is an empty set. All right? Question is it a subset of the set of natural numbers? Well, empty set is a subset of all sets. So therefore, what is that argument? So this is yes. All right? So that means natural numbers includes all its accumulation points. Well, that's weird, right? There's no accumulation point, so the set of accumulation points is empty set, but it's included in the set of naturals. So therefore, by logical deduction, the set of naturals is a closed set. All right? So set of naturals is a closed set. Well, by the way, with similar reasoning, the set of rational numbers, real numbers, it's also a closed set, right? Okay, so some people kind of think that these two arguments, closeness and boundedness, are sort of related. They logically imply one another, but the true answer is that they're logically independent properties. Meaning there are some sets which are closed but not bounded, but bounded but not closed. All right, very simple example. So the 0, 1 open interval, this is clearly not closed. All right, but we know that it's bounded because the farthest distance between any 2 points in this interval is just 1. So it's bounded. But it's not closed, all right? Set of natural numbers is closed, as we just argued, but it's not bounded, all right? Because the limit point, I mean the maximum point, right, is not the infinity, I mean, is not there. It's not an element of set of naturals, so therefore it's not bounded. All right, so one final definition is compactness. Compact set. So especially in set of reals, so let's say sets, let's use the same notation. S is a subset of Rn, all right, is closed and bounded. Well, then S is compact. This is a definition, all right? And every definition is an if and only if statement. So what does that mean? That means if S is a subset of Rn, is closed and bounded, well, then it's compact. And if it is compact, well, then S is closed and bounded. All right, so that's a definition whenever S is a subset of Rn. All right. Well, why compactness is, well, example, 0, 1 closed interval, right? This is closed and bounded, so it's compact. However, set of naturals, it's closed but not bounded, so it's not compact. So this is not compact. This is compact. All right, very well. Why compactness is important? Because compactness ensures us that the optimization problem has a solution. All right, so the existence is an important issue. So if you are trying to maximize a function over some domain, and if you're not sure if the max or the min exist, well, then searching for max and min sometimes may be like searching someone in a dark room. All right, you don't even know if there is someone there. All right, so you don't even have a hope. So thanks to Weierstrass theorem, what we know is that if f is a real valued function from S into R, where S is a subset of Rn, and f is continuous function on S, and S is compact, right? Well, therefore, there exists x star, x double star in S, such that the following argument is true. F of x star less than or equal to f of x less than or equal to f of x double star for all x is an element of S. All right, so what does that mean? That means if your function is a real valued function defined over a subset of Rn, the simplest scenario is S is a subset of R, like 0, 1 closed interval. If f is a continuous function, there's no jump up or jump down. S is a compact subset, meaning it's closed and it's bounded. Well, then you know what? There's always a minimum value of this function, global minimum, and there's always a global maximum of this function. We're not talking about local minima, local maxima, but the global minimum and global maximum do exist of this function. All right, thanks again to Weierstrass theorem. So therefore, if I know my function is continuous, if my domain is compact, well, then I know that min or max problem has a solution. So the question is, how am I going to find those min point or the max point, the maximizer or the minimizer? So this is what we're going to learn next, the optimization.